but I think it's time to start already, so I will start. Thank you for coming, and the first thing, let me, on behalf of C++, apologize that I even need to make a talk on this title, because this should be kind of obvious, but have material more than enough than for 1 hour and even more than that. My name is Mikhail Matrosov. I'm a tech lead at Pinally. Pinally is a privately owned algorithmic trading firm situated in Cyprus, Singapore, and the Netherlands. And at Pinally, we trade all kinds of assets on all kinds of exchanges all over the world. I personally live and work in Amsterdam. And I am a C++ enthusiast. I'm a public speaker. And I like to call myself a software complexity manager, because I do believe that really a lot of problems in software development stems from unmanaged software complexity. And you can always talk with me about personal finance, crypto, science and tech, bikes, and travel and hiking. During this talk, if you need to make a clarification about what I've said, meaning that you cannot follow the talk, something is not clear, just raise your hand, please ask immediately. If you have any kind of question which does not affect your ability to follow the talk, please hold it till the end. That's the regiment. During this talk, I will mention a lot of specifiers, qualifiers. I will talk about storage duration and linkage. If you want to know more about this topic, I invite you to watch my talk on this dedicated matter at using.studcpp conference in Madrid, beginning of this year. The recording is available on YouTube. All right, let's start. What is a constant? For the purpose of this talk, we will define a constant as a variable whose value does not change and does not depend on runtime. Meaning, if something is a constexpr, this is by definition a constant, because it is not compile time and it's not going to change. For instance, this set, which is not constexpr, is also a constant according to our definition, because it's known at compile time, it's not going to change. However, this const qualified int count is not a constant, because obviously it depends on runtime. And now let's start forming our guidelines on how to declare a constant. The first item, use constexpr whenever possible, otherwise use const. Obviously, we want thing to be const qualified, because it is not going to change. Why constexpr? Because it clearly expresses your intent. You're stating this thing should be known at compile time, and yes, make sure it is known at compile time with constexpr. It gives your compiler more optimization opportunities, and it saves you from static initialization order fiasco, which happens when you initialize a global variable from one translation unit, and you depend on the variable of some global, on the value of some global variable in another translation unit, which might happen not to be initialized, because the order of initialization of these guys is not determined. So this is our first item. Now, we will cover different scenarios in which constants may appear. And the first scenario is local constants. All right. Let's take a look. We have a fixed string class, and a fixed string is just an example of something literal but not very trivial class. Here we see the function ping, which sends some predefined string, well, happens to be ping, and it calls the method send to do this. Do you have any concerns with the implementation of function ping? Anybody? Oh, this is the code you would write yourself. No hesitation at all. Yep. What exactly do you mean by that? Yes, the ping function is a pure runtime function. We call it during runtime from time to time, so it's normal that it is not constexpr. It's not a problem. The problem is that this string that we sent, it is known as compile time. However, if you see the assembly, by the way, who has at least some experience with assembly, who is not kind of afraid of it? Around half of the audience. I will explain. So basically, this is what your code compiles to. Not really, but basically, okay? And here we just call in the function send with some value, which should be known at compile time. And we see kind of 12 lines of code, which is not good. In these lines of code, what compiler does, it actually creates a new object of fixed string in the stack frame of your function. And then it calls it. But this object, it's not going to change. It will always be the same, because it consists basically of one string literal. So this is just waste of time, waste of processor resources. This is not good. This is not good. So let's do this. Let's extract this constant into a dedicated variable, and let's make this variable constexpr. Okay, now who thinks this will not be enough and we will still see this object created every time? One person kind of, or 2% kind of. Okay, this won't be enough, guys. It's basically exactly the same thing. We just refactored the code a little bit and we gave our constant a name. Now it is named SS. But if you expected that the compiler will somehow magically use the knowledge that this thing is constexpr and hence I should not create it every time the function is called, that's unfortunately not how constexpr works. You see? There is this very useful mental model, which is very simplistic, but I relied it and I never failed actually. You can think that your C++ program runs twice. First it runs at compile time with all the constexpr computation and stuff. And then it runs the second time actually when you run the binary. And during the runtime, the constexpr that you had, it decays to const. So if you want to reason about how exactly this program will perform at runtime, just in your head, replace constexpr with const. You will have the answer, most probably. And here, if we replaced constexpr with const, we wouldn't be such surprised that the object is created on each invocation of the function, right? So when we have a local variable, by default, local variables have automatic storage duration. That means new instance of a variable is created on each function invocation, which means multiple initialization and wasted CPU resources, not good. What can we do about it? Static, exactly. Let's do static. Let's add static here. Now it's static constexpr. And you don't need to know the assembly just to tell that this code is much better. So here we have just 2 lines of code for the ping function. What it does, we see the SS variable stored somewhere in static storage duration of the program, probably in data or arrow data section of our binary. And what ping function does, it loads the address of this variable to the DI register, which is used to pass parameters. And then it calls the send function. And it doesn't even call it, it uses jump, so it tailors tail call optimization. It is really good, really good. So here we fixed our function with this usage of static n. When we use a static on a local variable, this means the variable now has static storage duration, which means only a single instance for all function invocation exists, and we get exactly 1 initialization, which is great. Now let's try this thing. Let's say that our send method, instead of fixed string, now accepts std string, and let's say that the message is not that short. We actually need to format according to some rules of the server that we communicate with, or the client that we communicate with. Do you see any problems with this code? Do you expect any failures, maybe? It will not compile. Why? I'm using constexpr string outside of constexpr, and so what? We've been doing this on the previous slides. Yeah. Yeah, exactly. So here, this depending on your compiler, this string might not fit into small string optimization, meaning we will allocate some time at compile time, some memory at compile time. But due to the thing called non-transient memory allocation in C++, this won't work. We will have an error like this. Let's not go too deep into why we have this error. But the thing is, here we have an example of a class which is not literal. Okay, and we cannot use constexpr on that. So let's get back to the square one. We have the string, and now we use simple const. We have a lot of assembly here. What is happening is that on each invocation of function ping, we actually need to construct new toString object. We need to allocate memory for this object. We need to copy the content of the string literal into this object. A lot of work, and it happens on every invocation of the ping function. Not very good. We already know the fix, right? Let's just throw some static in here. Should help. So let's add some static. And oh my god, even more code. What happened here? Fear not. It's actually not that bad. Because you see, when you have a static local variable, you know that this variable will be initialized on the first invocation of the function, the first time the control flow reaches the declaration of this variable. And when it happens the first time, the compiler needs to actually make the initialization of the variable. And all other passes, it will use the initialized variable with no extra work. And what happens in the first 3 lines of the function, you can see this movesitx guard variable for ping ss. So there's a special guard variable stored somewhere in static storage for the compiler, for the binary. And the first thing that the program does, it checks the value of this variable. And if the variable is already initialized, then at line 5 we jump to line 14. At line 14 we have, well, basically exactly the same 2 lines that we had on the previous slide. We load the address of the variable, and then we call the send function. And this is what will be executed most of the time. And all the rest of the code will only be executed once on the first invocation of the function. So it's not that bad. Fear not, it's still pretty good. Let's add this line to our guidelines. For local variables, ensure static storage duration with static. Everything clear so far? Any clarifications? Okay, great. Let's move on. The second scenario. The global constants in CPP files. All right. Let's take a look at this program. Here we have 2 CPP files. Main CPP on top, other CPP on bottom. In both files, we have global constant ss in main CPP and in other CPP. And they are different, they have different values. In the main function, we first print the content of the first variable from the main file, then we call the function which prints this variable from the second file. And here on the right, you can see the output here, and the output is exactly as we expected. The value from the first file, the value from the second file, no problems here. We see that these variables, they do not interfere with each other, which is good. When we have a const qualified global variable, this implies internal linkage on this variable, which means this variable is not accessible from other translation unit, and everything's fine, and we're gonna have no ODR violations, no one definition rule violations. Looks good. Note the small asterisk here, however. What if our variable is now a template? Okay, so we have template in first file, we have the template in the second file, and we use exactly the same template instantiations into other files. And now the output is a little bit strange. Definitely not what we expected, and this really smells like some undefined behavior, because indeed we have ODR violations here. You see in this asterisk, this rule only applies for non-template, non-volatile variables, which is kind of odd, and that's probably not what you should think about that much. And the other thing is that ODR violation, you might have thought, all right, we have like basically two different definitions for the same variable, because the compiler starts to think, actually the linker starts to think, these variables are actually the same. So, all right, what's the problem? Either the value of one is going to be used or the value of another, but no, here actually in the second translation unit, the value of the first translation unit truncated to the length of the value of the second translation unit is used. This is undefined behavior. Anything can happen. We actually were lucky it didn't get worse. Okay. Note that we have exactly the same problem if we're using inline static data members for a class. When we have a constexpr static data member for a class, constexpr in this context implies inline. This is very useful, very convenient. However, we hit exactly the same ODR violation, because these guys, they do not have internal linkage. Instead, they have, in this case, external linkage. If you need to know more about these linkages and specifiers, yeah, I already pointed out to another talk. You can check this out. Right, so how can we fix this? How can we make sure we have internal linkage and the different variables do not interfere with each other? Anonymous namespace, exactly. So let's put this stuff, either the variable or the class itself, into an anonymous namespace. Now we have expected output, which is great. When we apply anonymous namespace, it guarantees that anything within the namespace has internal linkage. There's no way for stuff to escape from anonymous namespace, and it becomes inaccessible from other translation units, and we won't have any ODR violations, which is great. Let's put this item to our guidelines. For global variables and static data members in CPP files, ensure internal linkage with an anonymous namespace, or you can use static keyword for global variable, which will do the same thing, but anonymous namespace will work for both the variables and static data members. All right, everything's clear so far? Good, good. Now let's talk about global constants in header files, and this is where it gets really interesting. Let's consider this program. We have one header file on top, common.h, and we have two CPP files, main CPP file and other CPP file. And as you can see, not much happens in this program. Basically just both the files include this header. Can we expect already any problems with that program? Any unexpected behavior or result of the compilation? Sorry? Duplicate symbols? Duplicate symbols, exactly. So what happens here, this const string ss is included in both files. We have two different translation units with this symbol, and we already know that const qualified global variable has internal linkage, and each translation unit has its own independent copy of this symbol. If we look at the binary, at the assembly, what's interesting here is in line 6 and at line 13, we have these global sub main, global sub other. These are the code snippets that will be executed on program startup by the runtime. And you see how both are initialized, both are doing some work. This work is actually to initialize these two independent constants. We can also inspect the generated elf file with readelf, and we can read data and raw data sections. And in the data section, you can clearly see there are two objects. This string is duplicated, it's repeated 2 times. So we haven't even done anything. It is already bad. Let's try to fix it. First, let's follow our guidelines. We have the first item which says use constexpr. We can use constexpr here. Let's do that. Yeah, so I described that. The problems is that each independent copy requires initialization startup. Each occupies the space in the binary. We saw it in redelf. And the worst part, that each copy occupies its space in cache. So your program works. It uses different copies of this very same variable from different translation units. And from the point of view of the rest of the program, these are completely different variables. They all need to be loaded in memory, and they just waste your cache and increase cache misses. This is not good. Let's do constexpr. Wow, that's pretty good. The program does nothing, and you can see that there's basically no code, assembly code generated for it, which is great. And in the binary, nothing in the binary. So just by replacing const with constexpr, we gave the compiler enough information to perform the useful optimizations for us. And it was really, really good at it. So yeah, good approach. But that's also cheating, of course, because we do not use the variable. Now let's use it here in the main function. Let's do some calculations with this variable. And these calculations, they do not depend on runtime. And again, compiler was really, really good to perform all this computation at compile time. And in line 2 of the assembly, you see the line move AX some value. EAX is the register that is used to store the value returned from the function. The function main returns, this is the value, the result of our expression. All right. Now let's do some runtime computations, okay? Let's do it like this, and now we access SS with some runtime index. Still pretty good assembly, but now we can see how compiler was forced to actually put the content of a string into the binary, because yes, we need to have it. We do not know beforehand which symbol the user will access. So yeah, but the assembly is still pretty good. But that's still a little bit of cheating, because we do not use it from the second translation unit, right? Let's use it from the second translation unit. And now, okay, who thinks that now that we use it from both translation units, we will still have duplicates in the binary? We will still have 2 objects in the binary. One hand, 2. It's pretty shy. Of course we will. I mean, come on, we've been through this. Now we have two of these guys in the binary. Now, yes, the string is constexpr, but now we're reasoning about the runtime behavior of the program. What you do when you need to reason about runtime behavior, in your head, replace constexpr with const. When you do that, still, you have 2 translation units. They're independent. They work with the independent copy of the variable. And yes, this particular variable happens to live in the read-only data section of the binary, which is great. The compiler was able to put it there thanks to the constexpr keyword, but still we have 2 objects, and all the problems will repeat itself. So yeah, how do we fix that? Inline, yes, of course. Let's add inline to our variable, and now we have inline constexpr. The code is still pretty good, nothing changed, but now we can see there is exactly 1 copy of the variable in the binary. Yay, inline worked. What is inline? When applied to a global variable, it implies external weak linkage, which, by the way, is not a real linkage from the point of view of the language. There is no such thing as weak linkage. It's only internal, external, no linkage and module linkage. But this is a very useful concept in the world, and actually when you examine the content of your generated object files with tools like NM that will explicitly tell you the linkage of particular symbols, they will, for this SS variable, they will tell you the linkage is weak, because it is very useful for this particular case. It basically tells the linker that yes, you will see this symbol in multiple translation units. Don't worry, just assume they're exactly the same and use one of them. And that's it. It's pretty easy. Now we have single copy for all translation units, no extra initialization, no extra space in binary, and no extra space in cache. Yay. Except, well, what if, again, we cannot make it constexpr? For instance, it's too big, and here, of course, you have to understand this. String here is just an example of any type that is not literal. Just use your imagination, put anything you want here. It's just for the purposes of the presentation. Let's get back. Let's make it const. Okay, what do we have here? No inline here. Just wait a little for inline. What do we see? We see, again, two code snippets. Global sub imain in line 7, in line 25, global sub other. These are the snippets that will be executed on the program startup by the runtime. And you see quite a lot of code here. This is the initialization of the string with dynamic memory allocation because it doesn't fit into the small string optimization buffer. And you can see the call to operator new in line 10, for example. You see there is dynamic memory allocation happening. And it will happen twice when you run your program, which is not very nice. All right, we already know what to do, right? Let's add inline, should help. We add inline, and oh my god, even more code. Again, let's zoom in a little bit on the generated assembly. Now there are two snippets, one for the main, one for the other, and they are actually very similar. They are indeed the same. By the way, you can even in lines 8 and 30, at line 21 and 43, you can see the address of the variable that is used. It is 404060 in the main and is again 404060 in the other. So they work with exactly the same variable. But we do have two pieces of code of the assembly. What's happening here? You see, both start with exactly the same thing called guard var. It's actually a guard variable. Now, what happened is that we execute both snippets, but only one of them will run. Only one will perform the initialization. It will set the guard variable, and when another snippet is run, it will check the guard variable, and it will do nothing. Because you see, these snippets, they have to be generated by the compiler. Compiler works on the level of independent CPP files, independent translation units, right? So it cannot know in which translation unit exactly this variable will be initialized. So that's what it does to overcome that. Then the linker goes, it sees two snippets, no problem, just stitches them together, and this is what we got. But we don't really like it that much. We would like probably not to have duplicated initialization code in our binary, even though only one of it will run. Maybe there is something we can do with it. Any ideas? This is the problem that cannot be resolved at compile time. Okay? This is some kind of optimization that can only be done at link time. And this feature is called link time optimization. All right, so let's enable link time optimization with -f LTO flag. Now we have that indeed we only, well, the structure changed a little bit because of the optimizer, but now we have only a single snippet of code that will initialize our variable, which is good. So we can say that, yeah, inline, the same slide, no extra space in binary. It might depend on your compiler flags, but generally it's still pretty good. And if you really care about your binary size, well, yeah, you might want to use -f LTO flag for that. All right, so let's add the next item to our guidelines. For global variables and static data members in headers, ensure weak linkage with inline. And by the way, if this is a static data member, which is constexpr, inline is implicit. You don't need to spell it out explicitly. All right. Now let's talk about this stuff. Global constants in headers with detached definition. Sounds pretty cool, but in fact it's actually pretty easy. So imagine we have this thing. We have some data. For instance, I know it might be generated lookup table or some pre-computed stuff or whatever. The thing is that to compute it, it is either a very complicated expression or it's actually just pretty expensive to compute. When you write it like this and when you put it into a header file, this means that this expression, it actually will be compiled in every translation unit, which might ruin your already pretty bad compilation times, and I'm sure they are bad. I know this. I don't even ask you about that. Then you might have some implementation detail exposed because it's just the way you populate the structure. Don't really want others to think about it and to know this, and it potentially can bring some additional dependencies. For instance, this expression might call some constexpr functions which are not used anywhere else. Why would you expose them to the users? So what you can do in this case, you can split the definition and the declaration of the variable with the help of extern. In the header file, you only write extern const data, and this statement is actually a variable declaration. And now you need to, somewhere in your program, you need to provide the definition for this variable, which you do with, well, exactly the same line, constexpr data, and you define it. And now it is purely in this CPP file. So when you apply an extern to the variable gets external linkage, and you might detach declaration definition. Sometimes it might be very useful. Now, the initializer during the compilation time is compiled only once in this particular CPP file. Implementation detail hidden. No unnecessary dependencies. You can put everything into this CPP file. Will be good. A little problem is that the data no longer appears constexpr in other translation units that include this header file. However, the variable itself is still constexpr because see, in the CPP file, we used constexpr for it, even though in header file, it is const. It is allowed to do that. It's great. So if your code, if your clients, the users of this data variable, do not rely heavily on the compile time optimizations based on the specific value of this variable, then this might be a really good transformation for you. So yeah, we detach declaration definition for a variable with the keyword and specifier extern. And there is another way in C++ to separate declaration and definition of a variable. What do you think it is? Oh, that's actually, I'm pretty sure you know it. Static data members. By default, static data members, if you don't use some inline constexpr magic, by default, they only declare variable. And then you need to go and explicitly define it somewhere else, usually in a corresponding CPP file. So you can do exactly the same thing for a static data member of this type. All right, so let's amend our guidelines a little bit for global variables and data members and show weak linkage, or move the definition to the CPP file. For that, you will need to use extern if this is a global variable. All right, so this is, congratulations, this is pretty much complete guidelines on how to declare the constant in C++, but we still have some time. Do you think, why do you think that is? we missed one important thing, modules. Of course, modules. Does anybody know this website, are we modules yet? Okay, one person is pretty good, tracks our current modularization of the most popular C++ libraries. Should be done in year 2298. But actually, when you looked at this website like a year and a half ago, this progress bar was like 1 pixel width. So it's pretty good acceleration rate, right? Who has written at least one line of C++ code related to modules? 1, 2, 3, 4. 4 people, yeah, that's kind of the same. Oh, all right. Yeah, you need to have a module supporting compiler. That's true. All right. So I feel like we need a little bit of modules 101 slide. This is, of course, an oversimplification and really terse information, but I think it will help us to answer the question at least how to declare a constant. It might be useful for you to reason about anything related to modules, because it's really high level and omits a lot of details. So first, module unit is either a module interface unit or a module implementation unit. So when you have a special file, C++ file called a module unit. A module interface unit is kind of similar to a header file, but it is imported, it is not included. This is a totally different procedure. And it is a separate translation unit, unlike a header file, we just included in different other translation units. And you have module implementation unit, which is kind of similar to a CPP file, but everything is contained within this module. And module implementation units for different modules, they cannot affect each other, which is pretty good. A module implementation unit is still a translation unit, so everything we said about the translation units applies to module units, which means that a translation unit is either a module unit or a regular non-module translation unit. Makes sense, they kind of split here. Basically, if you had any entity with external linkage in a regular translation unit, and you take it and put it into a module unit, instead of external linkage, you will have module linkage. And module, if an entity has a module linkage, it can only be referred to from within the same module. And this is how you do this modularization, separation, and module independence, component independence, which everyone is so happy about. Now, if you want to have external linkage in the module world, meaning if you want to have entity available from other modules, then use the new keyword expert. All right? Now, the very important thing is that the concept of a weak linkage, this was never a real linkage, this was a useful concept. Well, it is no longer useful in the world of modules, which is actually a good thing, because from the start, it's kind of a hack that helps us understand the hack that deals with the fact that header is included into multiple CPP files. So this is a good thing. Now the last part might be a little bit tricky, so I will skip it. You can photo and just go through it if you wanted some technical jargon here. So let's see what changed. Mostly things are more or less the same when it comes to the linkage and sense of the variables. But what changes is now we can use expert on the variable to force it to have external linkage. And now if we are in the module interface unit, and let's say we have a const qualified constant without any additional specifiers, it would get internal linkage in a header file and a CPP file in a regular translation unit, right? We discussed that multiple times. But in a module interface unit, it will instead get module linkage. And this is a pretty sensible default, I would say, because when you declare a constant in a module interface unit, probably you don't want it to be of internal linkage because, well, it's in a module interface. That's an interface. Makes sense. Why do we even need modules? And among other things, because modules promise faster compilation and they promise less ODR violations, right? This is pretty funny, this less ODR violations. I love that. Let's take a look at this program with modules. We have our main CPP file, which is not a module, by the way, which declares this constant SS, which is static constexpr data member. You already know that there might be some problems here with interference with another translation units. We have our module interface unit for module M, which exports two functions foo and bar, which are defined in two module implementation units, number 1 and number 2. And both module implementation units for the same module M, they have exactly the same constant, defined as a static data member of a class. So the function foo from the first implementation units prints the value of corresponding constant. Same happens in the second module implementation unit, in the function bar. And in function main, what we do, we print these constants from the current translation unit and then from these two module implementation units. All right. Now, who expects at least one ODR violation in this program? Not really sure. I would hope so. But yeah, this slide is here for a reason, right? If we compile and run this program, this is what we will see. Now, this is pretty interesting. So we still see an ODR violation, but this ODR violation is conveniently encapsulated in the module. Well, which is good. I would say that it doesn't get away from the module, and we have no interference with the constant defined in our main CPP file, but still kind of not nice, right? So we still have exactly the same problem with exactly the same ODR violations in two different module implementation units. So yeah, we indeed have less ODR violations that we used to have. Yeah, the fix is exactly the same, just add anonymous namespace here and you will be fine. All right, with that, we will make the guidelines how to declare a constant in a module unit. The first two items are exactly the same. Use constexpr whenever possible for local variables, ensure static search duration. Now the third item, for global variables and static data members of module implementation unit, which is kind of similar to a CPP file, and the recommendation is also exactly the same. Ensure internal linkage with anonymous namespace so you don't get ODR violations. It gets more interesting for the module interface units. So for the header files, you remember that you wanted to ensure weak linkage, but weak linkage no longer works, no longer useful in the world of modules. And what you need to do instead, you need to pick any other linkage but weak. So it is perfectly fine in the module interface unit have an entity with a module linkage or external linkage or internal linkage. It's just whatever fits you. If you want to export it, use external. If you want to use it within the current module, use module. If you want to use it only to define other stuff in this interface unit, use internal. No problem with that. So the recommendation is the opposite. And when it comes to static data members of the module interface unit, well, I guess a little bit tricky. The syntax you should use is exactly the same as you used in non-modules world. Use either static inline const or static constexpr, depending on what you can use. Of course, by default, prefer constexpr. And this would imply weak linkage in non-modules world, but we're in the modules world. It no longer works. So the thing is, don't think too much about the linkage of static data members in a model interface unit. Instead, pick appropriate linkage for the containing class, because actually what happens, the linkage of this static data member will be the same as the linkage of the containing class. And this you can do with the same things, expert or anonymous namespace or modulus by default. Right, that's, yeah, congratulations. These are the guidelines for the model units. Now we have a little bit more time, and yeah, I want to go to the basement and tell you a little bit of fun story about const init. So who knows what const init is? Yeah, a couple of people. Well, basically const init is constexpr minus const. So when you have a variable which is not supposed to be const, you want to modify it in your program, but you want to ensure its initialization is done at compile time, you declare it const init. So it is constexpr minus const. And it kind of seems that it doesn't make sense to declare a constant with const init, because it moves away the const, right? That's just strange. We would need to just rearrange the terms of the equation. We would need to use const init plus const, which we will do. So imagine this example. It is actually like an extract from the real world code base that we use in our project. We have this intricate thing. Let's say we have a mixin class, which is parameterized with some base class, and it wants to declare a constexpr constant of this base class, right? And then we use it in this CRTP style, or we can actually make it even a member of the struct A. It's not a problem. And the thing is that, well, on top you see the output of GCC, on the bottom the output of Clang. GCC is fine with this code, it compiles just fine. Clang is not. Clang isn't happy, and it's not happy because this base in the mixin is supposed to be A, but at the point where it is used, it is not complete, so it's not happy. I'm not sure which of the compilers is wrong. I actually don't know. Maybe we should report a bug somewhere. So I assume some of them is wrong, but the thing is, when we try to use it and we do compiler code with both compilers, CI didn't work. We need to do something about it. And what we came up doing was this. So we do have this restriction for constexpr, but if we split it into const init const, and it is no longer inline by default, so let's add some inline here, it works, and both compilers are fine with that. I think it's just hilarious. I wanted to share. Thank you guys for listening. This is what we have in a couple of places in our code base. I really hope that you won't need to write something like that, but yeah, somewhere it exists. Just live with this fact. So with that, thank you very much. And here is the QR code with the link to this very presentation. The presentation, the slides with the screenshots from Compiler Explorer. In the footnotes of the slides, you will find the link to the exact layout of the Compiler Explorer. If you want to reproduce it, if you want to play with it, check out the compilers, compiler options, just feel free to do that. All right, any questions? Yes?
Okay.
Okay.
You said you can solve
Yes. This slide again. Yeah, probably this one.
But technically, with C++23, you could compile allocate the std array as a storage for that string, then declare it a static constexpr at some point, and then you can return it as a string.
So the comment is that this particular thing we can rewrite in a way we won't have this duplicate initialization and different translations. Yes, you are perfectly correct. The thing is, you can do this for a std string, but remember I said this string is just a placeholder for any kind of type which is not literal. So I agree, for string, this is a little bit silly, but for any other type, yeah, the same logic holds. Thanks. All right, if there are no more questions, thank you again.